this video, we're going to look at the Module 15 Sas Code. So you'll notice the screen here looks a little bit different than it typically does in these videos. Usually I make these in the recording studio on campus, but campus is closed. So for this last video, I'm going to be making this on my home PC, so the audio quality might not be as good as it normally is. Alright, so we always want to start by making sure we have all of the information that we need. So for this video, you're going to need your data set, the Module 15 SAS notes, as well as the Module 15 SAS code. And also not pictured here, you're going to want to make sure that you have the code book for the data set as well. Alright, so let's start out by looking at the notes. So in Module 15.1, we looked at different hypothesis tests for quantitative variables. We're going to look at some of those hypothesis tests in this video and see how to perform them using SAS. And what you're going to see is this is going to be very similar to when we created confidence intervals, as well as when we did hypothesis tests for categorical variables. And the first hypothesis test that we're going to look at is the one-sample t-test. Now, one-sample t-tests are very useful when you're trying to answer a question about a population mean and compare that population mean to some known value. And usually this will be some historic value or value that's important in context of that particular variable. So for example, we could ask at the 5% significance level, is the mean BMI for people living in Kentucky during the year 2018 greater than 25? And so notice here we are asking a question about a population. We don't have population data, we only have sample data. And so what the hypothesis test does is it allows us to take the information contained on our sample to see what we can say about the population. And in particular, we're going to see if we can prove the population mean BMI is greater than 25. So let's go and look at the SAS code and see how we can do this. So I've got the SAS code pulled up here. And remember, the very first thing you always want to do with your code is read in your data set. So in order to do that, we need to make sure we've got the correct location with where the data is located. So I'm going to change this. And we'll go ahead and run this. Alright, looks like my data loaded. And so now we can see how to perform the one-sample t-test. Now, as with any of the inferential procedures you've learned about in this class, there are assumptions that go along with that inferential procedure. And in general, and in practice, you always want to make sure after you've chosen a particular method that you check the assumptions for that method. And all inferential procedures have assumptions that go along with them. So to check the assumptions for the one-sample t-test, one thing that we could do is we could check for evidence against normality. So in other words, if we know that the population or BMIs from the population are normally distributed, then we know that the one-sample t-test is appropriate. So here's the code to do this, and this is the exact same code when we looked at confidence intervals for a single mean. And so here was the histogram we got. Now remember, when you're making the histograms to check assumptions, we don't have to worry about changing the title or making it pretty. This is just to give us an overall picture of what's happening in the data. And based off this histogram, we can see that the BMIs are slightly right skewed. Now if this were a small sample, I might be concerned about that. But where sample size is so large here, that the central limit theorem takes over, and so based on the central limit theorem, it's perfectly fine that histogram has a slight right skew. We don't have to worry about that, again, because our sample size is so large. So we do meet the assumptions for the one-sample t-test. So to perform the hypothesis test, we're going to use the Proc T-Test function, and you'll notice for this function I've given it the data set. I've also given it alpha, so that's your significance level. Now in this case, we've got sides are equal to 2. So sides equal to 2, we want sides equal to 2 if we have a two-tailed test, but we want to have a right-tailed test. So let's see how we could do that. So to change it from a two-sided test, what we could do is add in L or U. L will do a lower tail test and U will do an upper tail test. So since we're testing to see whether or not BMI is greater than 25, we want to do the right tail test. Now, the other thing to notice here, if you'll remember from our confidence interval video, the way that the BRFSS codes BMI is there are two implied decimal places. So in other words, if we're interested in a BMI of 25, in the data set that would be coded as 2500. So you'll notice under the null hypothesis here I have 2500, and then I've specified the variable BMI. So let's run this. Alright, so that's going to give us a lot of output. Some of this output is actually there to help you check those assumptions. So for example, we haven't talked about QQ plots, but QQ plots are one way to check the normality assumption. And you'll notice here how QQ plots work, if you see these, is you have this line right here. If all of the points are pretty close to that line, that would suggest normality. But if they view it away in the tails, that usually tells you there's some kind of skew. And we already know that this data set is right skewed, and so this QQ plot here makes sense. But again, based on the central limit theorem, we see it here in this histogram as well, based on the central limit theorem, we know that we're fine even though that skew exists because our sample size is so large. All right, here's the piece of information that we really want though. This is the results from our test, and you'll notice they give us a summary or descriptive statistics from the sample. They also give us the confidence interval, and we had seen that before. And then down here is what we really want. So here is the t-value, that's the test statistic, and then here is our p-value. And so we can see our test statistic here is very large, and then our p-value here is very small. So if we go back to our notes, so here in our notes, you'll see I've copied and pasted that piece of the output and highlighted the piece that we need. I've got a little data note here about those two implied decimal places we spoke about. Since our p-value is small, we do have evidence here that for Kentucky in 2018, the average BMI is over 25. And so we have that here in our conclusion. Now, one thing that we haven't talked about yet, and you're actually going to look at in module 15.3, is the way that I've presented hypothesis test here is a fairly traditional one in the sense that we're comparing it to some significance level to determine whether or not our results are useful. And this is becoming an antiquated way to look at hypothesis test, but the reason I started this way was because most of the articles and things that you're going to read are going to present hypothesis test this way. But in the last several years, there has been this move away from using the significance level. And so you're actually going to read about that some in module 15.3. And the reason I bring it up here is an alternative way to do the conclusion would just be report the p-value and say the p-value in this case is less than 0.001, which suggests that we have evidence that the mean BMI of people living in Kentucky during the year 2018 is greater than 25. So in other words, you leave off the significance portion altogether. All right, the next hypothesis test that we're going to look at is going to be the two-sample t-test. Now, the two-sample t-test, what that t-test looks like is if you've got two different populations or two different groups of people and the same person can't be in either of those groups, and you're going to compare the mean between those two groups. Now you'll notice from your notes in 15.1 I have skipped over the paired t-test. The reason for that is the BRFSS data does not have any paired data, so we wouldn't perform a paired t-test with that particular data set. All right, so our research question we're going to look at here is, at the 5% significance level, is the mean BMI for people living in Kentucky with good, better health different than the mean BMI for people living in Kentucky with fair, poor health? And I've got a typo there. Go ahead and fix that. So notice I've got two different groups here I'm going to compare. I'm going to compare those with good, better health and those with fair, poor health, and we're going to see if the BMI between those two groups differs. So let's go to our Sas code again. And you're going to notice that this Sas code looks very similar to the Sas code when we looked at the difference in two means and created confidence intervals. So as always, you want to do a descriptive exploration of your variables first. That's always key. And again, the reason for that is that helps you check to see if you have violated any of the assumptions before using this particular inferential method. So what we've done here is we've just looked at that health variable in comparison to VMI. And when we do that, one thing that we notice is that the health variable takes three different values. So we've got the 1, the 2, and the 9. And the reason this is important is because we're only comparing two different populations here. So if we're comparing two different populations, we need to account for that third, or in this case the 9, which you'll remember that either accounts for the don't knows, not sures, or the refusals. So in your data set, you might have 7s and 9s that you need to take care of. All right, so what we're going to do is, since we're only interested in comparing the groups that correspond to the good, better, and the fair, poor health, we're going to remove the people that refuse to answer and the unknowns from the variable, or the health variable rather. So since I'm really only interested in the respondents that responded the 1 or the 2, everybody that responds something greater than 2, I'm going to set that equal to missing. And I'm defining a new variable here, and I'm just going to call it health. And health is going to store that information for me. And this shouldn't say calculate confidence interval. This should say perform hypothesis test. But again, the code is actually the same code that we used when we calculated the confidence intervals previously. All right, so we're going to use the Proc T-Test. We've got class equals health here, and again, the class variable, what that does is that's telling SAS what the two different groups that you are going to compare are. And notice that health now only takes two values, the 1 and the 2, and then the variable we're going to compare between them is going to be the BMI. So let's run this. So again, SAS is going to go ahead and give us some output that's going to help us check those assumptions. Here we have the QQ plots for the two different groups. And again, if we had evidence for normality here, what we would be looking for is all the points to fall on this line. And we actually have evidence against normality in this case because these points pull away from that line. We also see evidence against normality because when we look at each of the sample histograms, we see they are both right skewed. But again, our sample size is so large for the BRFSS, it doesn't matter that we have evidence against the population being normally distributed because the central limit theorem takes over, so we're fine to use this procedure. Now, if our sample sizes had been much, much smaller and we saw this, that might raise some concerns. All right, so here is our output here. In particular, the piece of information that we're interested in is this piece right here. Now, just like when we looked at the confidence interval for the difference in means, we had to decide for our inferential procedure, were we willing to make the assumption about equal population standard deviations or not? And so depending on which one of those you're comfortable with making that assumption, or if you feel safe not to make that assumption, that will determine which of these outputs that you use. So you'll notice that I have both of these highlighted. So in order to match with what went along with the confidence interval video, for this analysis, I'm going to assume equal population standard deviations. But again, generally the more conservative route is to not make that assumption, and that's the one you're going to see the most often in practice. And so you'll notice here, no matter which assumption we choose though, we do have an incredibly small p-value. So either way, we are able to show or conclude that the BMI between those with good, better health is different than the mean BMI for those living in Kentucky with fair, poor health. Now, one thing to notice here that you do want to be careful about is we have an incredibly large sample size here, so we're going to be able to pick up very small differences between those two. And so in fact, if we go up here and we look at our two different health groupings and we look at the mean between them, we can see that the mean between them here is about 200, but remember that because of the way that BMI is coded, that's really about a 2-point difference in BMI, which that does have clinical meaning. So you want to be very careful when you work with large sample sizes because you can get significant results in terms of the hypothesis test, but the difference that it's picking up can be very small. All right, so the next hypothesis test we're going to look at is the Anova. The Anova is very similar to the two samples t-test where we assume equal population standard deviations, but instead of comparing two groups, it allows us to compare more than two groups. So for this particular one, we're going to look at the variable smokeless tobacco use, and our question is, at the 5% significance level, does the mean BMI for people living in Kentucky, and that is in 2018, differ with respect to smokeless tobacco use? So again, let's go to our Sas code. All right, so the very first thing we want to do is we do want to look at that variable smokeless tobacco. to see what's going on with that variable. And to do that, I'm going to go and look at the code book. So here's our code book. So let's go and look at the smokeless tobacco. So here is this variable. And notice this variable takes 5 different values. So we have everyday use, someday use, not at all, don't know, not sure, and the refused. And so what we're going to do for this analysis is we're going to focus on these 3 responses, the everyday, the some days, or the not at all. And just like we normally do, we're going to actually remove the don't know, the not sure, and the refused. And then in your actual analysis, you'll want to document that removal. All right. So again, let's explore that variable, very similar to how we've done this before. And what you'll notice here is we're going to get some output for each of the possible values for that smokeless tobacco variable. And so for this particular case, I didn't have any responses that were a 7, but your variable for your data set might. All right, so again, I'm going to remove those responses that refuse to answer and the unknowns. Now, in this case, I'm interested in the values 1, 2, and 3 from this variable. So you'll notice everything greater than 3, I'm going to set to missing. So very similar to what we did in the previous example. And then finally, I'm going to perform the Anova test. To do that, I'm going to use the Proc Anova function. I've given it my data set. Similar to before when we looked at the 2-sample t-test class here, what that is going to do is that's going to tell SAS what the different groups are. So we've got those 3 levels for the smokeless tobacco. I'm going to feed it a model. So what the model says is I want to explain BMI based on what type of smokeless tobacco use a person has. And then we've got this last line of code here, which is means. We're going to look at the means for each of the different smokeless groups. And then these right here, we'll talk about them in just a moment. So let's run this. All right, so we get some different pieces of output here. Let's go to the top of the Anova procedure. So if you'll recall from the notes, Anova tests are always going to report the results in what is called an Anova Table. And so here is that Anova Table. And so if we go and we look at our Sas code, oops, sorry, I went down too far there. As I was saying, I went down too far. It's not this Anova table we want. We want the one here. Sorry, under Anova procedure. Notice here we've got a Anova table, and so our results are always going to be reported in an Anova table. And the piece of the table that we're interested in is this piece right here. So this is going to give us our test statistic as well as our p-value. And so for the Anova test, your test statistic will be an f-test, or it'll have an f-test statistic. And there's your p-value. So again, if we go and we look at our SAS notes, you'll see that I've copied that piece of information here. So our p-value, our f statistic is 3.09 and our p-value is 0.04. So this suggests at that 5% significance level that our results are significant. Now, one thing that we haven't talked about yet is, again, making sure that we test to see, or we look to make sure we check to see if all of our assumptions are met. So for the Anova test, some assumptions that you want to check are your normality assumption as well as your equal variance assumption. So the equal variance assumption, and this is equal population variances or equal population standard deviations, you can generally check by using side-by-side box plots. So we have the side-by-side box plots here. Looking at these box plots, they look reasonably close to one another in terms of spread, so I'm not too concerned about the equal population standard deviation. Now, you do want to be careful because you could also perform a hypothesis test to see whether or not there's a difference, and you want to be very careful in doing that when you're working with very large sample sizes, because again, if your sample size is very large, you're going to pick up very small differences between those, and it might be that difference is incredibly small, and so it's not really violating the assumptions of the Anova test. The other thing that you want to check is normality for each of the groups, and you could do that by making histograms for each of them or looking at QQ plots that we saw before. The Anova test is fairly robust to that assumption, so as long as you don't have wild deviations from it, you're generally going to be okay. All right, since the Anova test was significant, what we could do is next look at the pairwise comparisons. And to do that, you can just add in a Tukey comment here. So in general, anything you put after here, that's going to be additional test or additional output that you're going to get. So let's run this again. All right, so here is the Tukey procedure, and what the Tukey procedure does is it looks at all the pairwise comparisons to see where there's a difference. So the Anova test only concludes that a difference in the means exists somewhere. It doesn't tell you where that difference is. And so let's look at the Tukey's comparison. So what we're doing here in this column is it's looking at all the pairwise comparisons. So notice we could compare 1 to 3, 1 to 2, 3 to 1, 3 to 2, 2 to 1, and 2 to 3. And so in the SAS output, it actually looks at the ordering of the difference. So really the 1 to 3 and the 3 to 1 is containing the exact same information. The only difference is the direction. So if we look at that difference in means column, if we took the mean BMI for those who replied 1 to those who replied 3 and we looked at the difference, we would get 88.08, but if we flip the order, it would be negative 88.08. So really the information for this row and this row are redundant. So if we're going to try to figure out if there is a difference or where that difference, we've already proven with the Anova there is a difference, but where that difference occurs, one way to do this using Tukey's is to look at the confidence intervals, and if a confidence interval does not contain 0, then we can say there is a difference. And one of the reasons I chose this example is if you look at all of these confidence intervals, you will notice that they all contain 0. So this doesn't happen very often. Most of the time, if you perform an Anova test and the Anova test is significant, when you go on to perform the pairwise comparisons, you will find that, at least 2 of those means are different, and you can actually see where they are using the Tukey's test. Occasionally, you will get a significant Anova test, but when you go to the pairwise comparisons, you can't find where that difference is. And so this really highlights the idea that, there are many different inferential procedures to use, and many of them are used together or in conjunction with one another, but that doesn't mean that their results are always going to be matching or meshed together, because they really are 2 different tests. So in this case, I would just report that the Anova test was significant, and this really highlights the idea of what you're going to talk about in Module 15.3, that by reporting the p-value, it makes more sense than just saying the significance level. Because for this particular example, we found that the Anova test was below the significance level, but none of the pairwise comparisons were. Whereas if we move away from that idea and just report what the p-values themselves are, that makes a more cohesive argument. And again, you're going to read more about that in the next module. All right, so we've got one more example to look at here, and that is going to be our linear regression example. And what you're going to find is the code for this one is exactly the same as what we did in Module 9 when we built the regression line. And so our question here is, does the simple linear regression model with height as a predictor do a good job at explaining the variability? And that should say of weight. So let's fix that. And then further, is there evidence that the slope of the line is non-zero? And if it's non-zero, that suggests there is a linear relationship. All right, so the code, again, is exactly the same as what we ran in Module 9. So this code is going to build the scatter plot, it's going to build the regression line, and as part of that, it goes ahead and performs that hypothesis test. So let's run this. So you'll notice here's your scatter plot, there's your fitted regression line. We have some stuff here. This is to look at the residual checks that we talked about before. These fit diagnostics here, these are useful for checking the assumptions for any regression test that you're going to perform. And so SAS does a good job of kind of giving you everything that you need in order to check assumptions. If we come up here and we look at the output, you're going to notice there are 2 sets of test statistics and p-values. There's this one right here that gives you the F value and the P value, and this is summarized in an analysis of variance table. This is the output you want for the first hypothesis test. And then the section on parameter estimates, notice this has some t-test with p-values. This is what you want for the second hypothesis test. So again, we're going to go and look at our notes, and you'll notice I've copied and pasted both of those pieces of information. So again, the F-test, that is used to look at the overall model. So in other words, does the simple linear regression model with height as a predictor do a good job explaining the variability of weight? And here we see the p-value is small, so it does. And then the second set here, this is the one that looks at if there's evidence that the slope of the line is non-zero. And again, since our p-value is small, we do have evidence of that, and that suggests that there is a linear relationship between height and weight. Now, for simple linear regression, that seems a little bit redundant. I mean, it is two different questions, but what I'm going to probably talk about this just a little bit in Module 15.3. One of the things we don't learn about in this class is multiple regression. So in regression, we're not restricted to a single explanatory variable. We could have many explanatory variables. And so that's where the difference in these hypothesis tests becomes really important, because in the first one, you might look at an overall model that has a bunch of different explanatory variables. But then when you move down to the next set, you might be looking at those explanatory variables individually and determining which ones are in the model. All right, so that's going to conclude our Module 15.3 video. As always, if you have any questions or you need any help with the code, please let me know.